With chapters 5, 6, and 7, we are going to build on the concept of standard deviation and how we can apply that to then begin making some very basic inferences about our data. It still falls in the descriptive statistics components, but it allows us to see the data a little more clearly. So we're kind of building on each chapter. So for chapter 5, 3 basic areas: understand the z-score and how it relates to our location in the distribution, how to transform an x value into a z-score, and how to transform a z-score into an x value. Tools that you're going to need for chapter 5: the mean, the standard deviation, and your basic algebra. So what's the purpose of this z-score? Basically, it allows us to identify and describe the location of every score in our distribution. The key piece is that it allows us to standardize an entire distribution, and we can take different distributions and make them equivalent and comparable. So here's an example. 2 exam scores. Okay? The average was 70, you can see for both. However, with this test, the standard deviation was 3, and with this test, the standard deviation of the population was 12. So you can see one standard deviation above was a 73 in example A. In example B, one standard deviation above was an 82. So if you made a 76 in this class, wow, you did awesome on the exam in comparison to everyone who took the exam. If you made a 76 in example B, you were about halfway through the standard deviation of the class. So you were more close to average. Here you were way above average. So having that standard deviation that we calculated last week is a key piece in understanding exactly how much variation does our data have, and that can tell us a lot. So we can describe an exact location by a z-score. The sign tells us whether it's located above or below the mean. So you can have a positive z-score, you can have a negative z-score. And the number tells the difference between the score and the mean in standard deviation units. So a z-score of 1 is 1 standard deviation above the mean. And that can vary depending on your data. Like in the last example, that could be 3 points or that could be 12 points. But we always know one z-score, a positive z-score, is 1 standard deviation above the mean. A z-score of -1 is 1 standard deviation below the mean. So here's an example as it lays out on a graph. So this is a population. So our population average here, a standard deviation of 1 has a z-score of +1. 2 standard deviations would have a z-score of +2. So if our standard deviation is 3, a z-score of +1 we know is 3 points above the score. A z-score of +2 would be 6 points above our average score. Okay, so again, it just gives you this ability to see the data very quickly. Okay, so a learning check. A z-score of +1 indicates a position in the distribution. Take a few minutes and think about what we just discussed. Okay, and it would be above the mean by a distance equal to 1 standard deviation. Okay, so let's look at this learning check. Okay. A negative z-score always indicates a location below the mean. Is that true or false? A negative z-score. And a score close to the mean has a z-score close to 1. The first one is true. Okay, a negative z-score is going to be below the mean, so it's got to be a score lower than the mean. The second one is false, because if you have a score that's very close to the mean, your z-score is going to be 0, because remember, a z-score of +1 is 1 standard deviation above the mean. Now here's the equation for your z-score, and it looks a little scarier than what it really is. Okay? Really, it's your z-score equals the value, okay, the score you're looking at, minus the population mean divided by the standard deviation. Okay, so the numerator is a deviation score, and the denominator represents the deviation in standard deviation units. Okay. Now, using basic algebra, you can transform this. What if you don't know the z-score, but you know the z-score, but you don't know your x? You can algebraically solve for x, okay, by just rearranging your formula. All right, so let's say we have a population of 50 and a standard deviation of 10. What is the x value corresponding to a z of 0.4? Okay, now you can kind of do this in your head. 0.4 is close to 0.5, which is half, right? So half of 10, a half standard deviation. Okay, you could also look at it as percent. 0.4 is 40%. 40% of 10, how many points? That's 4. 50 plus 4 is 54. Okay. All right, so let's look at this example. If we have a population mean of 40 and 50 corresponds to a z of plus 2, then our standard deviation has to be 10 points. Okay. Now remember, plus 2 would mean 2 standard deviations above, so that would be 20 points. Okay. If a population mean is 20, a score above the mean by 10 points will have a z-score of 1. Okay. They're both false. If z is plus 2, then 2 standard deviations equals 10, so standard deviation equals 5. The second one is false because if standard deviation equals 20, then the z-score would have to be 0.5. So again, plugging those numbers into that formula. So every value, think of it with the exam scores, every value can be transformed to a z-score. Okay, the characteristics of when you do that, if you transform all your scores into a z-score, you get the same shape as the original distribution. Okay? The mean of the z-score distribution is always 0, and the standard deviation is always 1. Okay? A z-score distribution is called a standardized distribution. So those are the basics for Chapter 5. Again, the key thing is knowing how to take your value and put it into a z-score. And what's the benefit of a z-score is it standardizes everything. In your mind, you can see a z-score of plus 1. What does that mean? Okay, so that's the key piece to take away from Chapter 5. So with this in mind, let's move on to Chapter 6. We're going to understand the definition of probability. We're going to explain assumptions of random sampling, and then we're going to use the unit normal table to find probabilities. So the things you're going to need. You're going to need to remember fractions, decimals, percentages, basic algebra. Then you're going to need your z-scores as well. All right, so let's talk about probability. Okay, research usually begins with a question about an entire population. But in reality, many times we don't have access to the entire population. So actual research is conducted using a sample. Inferential statistics uses sample data to answer questions about the population. And the relationship between those samples and the population are determined in terms of probability. So that's why probability is so important, because we're going to take a sample and we're going to try to use that sample to answer questions about the population. And in order to do that, we really have to understand this concept of probability. Okay. So with the population, you take into account probability with your sample, and from your sample you can make inferential statistics. So you can infer what that would look like with the entire population. So first, let's define probability. It's when there are several different outcomes are possible, and the probability of any specific outcome is a fraction or a proportion of all possible outcomes. Okay, so the probability of A is the number of outcomes classified as A divided by the total number of possible outcomes. And we'll do an example, and I think this will make more sense to you. All right, so a small italicized p is the symbol for probability. The probability of some specific outcome is specified by p parentheses event. Okay? So the probability of drawing a red ace from a standard deck of cards could be symbolized by p parentheses red ace. So what is the probability of pulling a red ace out of a stack of cards? Probabilities are always in proportions. Okay, so we know there are 2 red aces the heart and the diamond, right? And there are 52 playing cards. So then our proportion is 0.03846. Okay? That's our chances, our probability of pulling a red ace from those cards. So let's talk about random sampling, independent random sampling. This is a process or a procedure used to draw samples, and it's required, absolutely required. This concept of random sampling is a big concept to understand. It's required for our definition of probability to be accurate. Okay? The independent modifier is generally left off, so we just call it random sampling. So what's the definition of a true random sample? It has to be produced by two main things. One is that each individual in the population has an equal chance of being selected. So it truly has to be random. It can't be, I'm going to survey all of the students in my class at Southeast. Well, that doesn't give every student at Southeast the exact same chance of being selected. Remember, that's a key piece. And the probability of being selected stays constant from one selection to the next when more than one individual is selected. Okay? It requires sampling with replacement. Okay? All right. So probability and frequency distributions. Probability usually involves populations of scores that can be displayed in a frequency distribution graph, which we've looked at in the last couple of chapters. Different proportions of the graph represent portions of the population. Proportions and probabilities are equivalent. So a particular portion of the graph will then correspond to a particular probability of the population. Okay? So here's just an example for you. Okay. All right. So a deck of cards, 52, contains 12 royalty cards, kings, queens, and jacks. If you randomly select a card from the deck, what is the probability of obtaining a royalty card? How would you set that formula up? It'd be 12 out of 52. Remember the number of things that you're looking for divided by the total number in the population. All right, so true or false? Choosing a random individual who walks by yields a random sample. Second one, probability predicts what kind of population is likely to be obtained. These are both false. The first one, because not all individuals walk by, so not everyone has an equal chance of being selected. Some people are at work, some people don't hang out in that area, so it can't truly be a random sample. It's called a convenient sample if you're only grabbing people that walk by. The second one, the population is given. So probability predicts what a sample is likely to be like, right? With probability, we're predicting what a sample is likely to look like. All right, so let's talk about probability and our normal distribution. Normal distribution is a common shape. It's symmetrical. You always have the highest frequency in the middle, and then the frequencies taper off towards the extremes. Okay? It can be defined by an equation, and it can be described by the proportions of area contained in each section. And z-scores are used to identify those sections. Because remember, z-score standardizes our distribution. See how all of this is kind of coming in and connecting now? Okay? So here's an example. In a normal distribution, my mean is here of my population and then a standard deviation. I know one standard deviation is a z-score of +1. Okay? You do not have to know this formula. This is just to show you there is a formula for how we get to this, but you're not required to know that formula. All right, so if we look at a normal distribution with z-scores, we know in a normal distribution that 34.13% falls within this area. Okay? 13.59% falls between a +1 and a +2 z-score. A z-score of above +2 is 2.28% of our sample. Okay, fall up there. So if you have if you take an exam and I tell you you were at a z-score of +2, you should be very proud of yourself because you're at 2.28% of the group. Okay. So normal characteristics of a normal distribution. Sections on the left side of the distribution have the same area as the corresponding sections on the right. And because z-scores define the sections, the proportions of the area apply to any normal distribution, regardless of the mean, regardless of the standard deviation. And I hope you can see then that's why a z-score is so important, because we don't have to know the mean, we don't have to know the standard deviation. We can figure out the percentage just based on that information. Okay? So the proportion for only a few z-scores can be shown graphically. The complete listing of z-scores and normal proportions is provided in the unit normal table. I'm also going to provide you a link to that as well, so you don't have to continue to go back to the online textbook. So that will be available on the website. So here's an example. If I know my z-score, if I know I have a z-score of 0.25, okay, how you interpret this table, the proportion in the body is always the largest area. Okay, so this is the body, this is the tail, and this is the proportion between the mean and the z. So these are critical because knowing exactly what you're looking for is going to determine which column that you look at. So if I have a z-score of +1, okay, then if I want to know what percentage of the group made a score less than this, then I would look at the proportion in the body. If I want to look at the proportion that made higher than that z-score, then I would look in the tail. If I wanted to know the proportion between the average and the z-score, then this is the proportion that I would find. Okay? So here's an example of proportions corresponding to a z-score or plus or minus 0.25. And the tail is, on this one, because again this is the bigger section, so we know this is the tail, is 0.4013, or about 40% fall here. If I look over here, the proportion in the body, 0.598, or about 60%. 60 plus 40, 100% of the distribution. Okay. If I look at a negative 0.25, then it switches. This becomes the body because this is the bigger chunk. So we have about 60% above a z-score of 0.25 and about 40% below a z-score of 0.25. So the unit normal table lists relationships between z-scores, locations, and the proportions in a normal distribution. So if you know your z-score, you can look up the corresponding proportion. If you know the proportion, you can use the table then to find a specific z-score. Probability is equal to proportion, if you remember all the way back. So the proportion of the normal curve that corresponds to a z of 1.50. If you look in the table and you find a z-score of 1.50, okay, you'll see that the proportion of the normal curve that corresponds to that z of greater than, okay, that's the key piece, greater than 1.50. So that's a positive z-score. Draw that normal distribution, put in the 1.50. It's going to be in the tail, correct? If we're looking at greater, if the z-score is greater. And then that gives you, I'm sorry, it's going to be the proportion in the body. That gives you a proportion of 0.0668. Again, that's the proportion in the tail that you're looking at, just 6% at a z-score above 1.50. All right. For any negative score, the tail will be on the right-hand side. True or false? Think about that. Negative z-score. True or false? If you know the probability, you can find the corresponding z-score. The first one is false. For negative scores, the tail is always going to be on the left. Right? And then the second one is, first, the proportion in the appropriate column Then after you find that proportion, read the z-score from the left of the column. So that's the key thing about probability. And for chapter 6, the key piece to take away is how you can find that proportion if you know your z-score, or how you can flip that around, and if you know your value, how you can find your z-scores. So next we're going to take that. We were looking at populations, right? Is just what we looked at. Next we're going to apply that to distribution of sample means. And here are the two basic learning outcomes. What's the definition of a sampling mean? And then we're going to describe a distribution by the shape, the expected value, and the standard of error. Tools you're going to need, again, it keeps building. Random sampling, the concept from chapter 6, probability and normal distribution, and then those z-scores. Okay. The location of a score in a sample or in a population, we know, can be represented by a z-score. So researchers typically want to study entire samples rather than just looking at a single score. So a sample provides an estimate of the population, and tests involving transforming sample means to a z-score. So that's why we're interested in that. Many times we're not just looking at a single score, we're looking at samples. This concept of sampling error, it's key that you realize that the error does not mean that we made a mistake. That's not what the concept is. Sampling error is simply acknowledging that there's a natural discrepancy of the amount of error between a sample statistic and its corresponding population parameter. So if we grab, say there are 100 students that are taking CJ425 this semester, and I want to survey 25. If I grab one sample of 25, and then I put those individuals back, I survey them, I put them back in the group, and then I grab another random sample of 25, they're not going to be exactly the same, right? There's going to be this natural discrepancy or this natural amount of error. And that's what sampling error concept is basically saying. Samples are variable. Two samples are very, very rarely identical, but we can account for some of that error. Okay. All right, so with that concept, distribution of sampling means the samples are going to differ from each other. Given a random sample, it's unlikely the sample means would always be the same. The sample means are going to differ from each other. The distribution of sampling means is the collection of sample means from all the possible random samples of a particular size that can be obtained from a population. Okay. So if we took, say, those 100 people and we surveyed them 1,000 times, gathering a random sample of 25, those sample means will end up looking like a normal distribution. Okay. Distribution of sampling means is called a sampling distribution. Okay. The sample means pile up around the population mean. If we have a true random sample, then most of the time our sample mean is going to be similar to the population mean. Okay. So this distribution makes a normal distribution shape. And the key concept to this is called the central limit theorem. It applies to any population with a mean and a standard deviation. Distribution of sample means approaches a normal distribution as n approaches infinity. Distribution of sample means for samples of size n will have a mean that is very similar to your population, right? So distribution of sample means for samples of size n will have a standard deviation that equals your population standard deviation divided by the square root of n. Now, in a nutshell, what this means is that the more times you sample a distribution, then the more likely you are to get a true feel for what the population is. And the larger your n, the more people you pull in, the more likely you're going to get your true mean. Okay? So, the distribution of sample means is almost perfectly normal, we find, if there are two conditions. One, the population from which the samples are selected is a normal distribution, or the number of scores in each sample is relatively large. We say at least 30. Okay? The mean of the sample distribution, or the mean of the distribution of sample means, I'll get that out here, and it has a value that's equal to the mean of the population. Again, we're saying if we have a truly random sample, okay, in theory, it should be very close to our population mean. So the mean of the distribution of samples is called the expected value of the mean. The mean is an unbiased statistic because your population mean is the expected value of the distribution of sample means. Okay? The variability of the scores is measured by the standard deviation. And again, this is of samples, not just one score. Now we're looking at multiple samples. Okay? Variability of a distribution of sample means is measured by the standard deviation of the sample means, and it's called the standard error of M. And it's written with the population symbol and then the M below. Okay? In journal articles or in other textbooks, the standard error of M can be identified as standard error or SE or SEM. The standard error of M is the standard deviation of the distribution of sample means. Okay? The standard error of M provides a measure of how much distance is expected on average between your sample mean and the true population mean. The law of large numbers, okay, is a key thing to keep in mind. The larger the sample size, the more probable, and think of that probability, the more probable it is that the sample mean will be close to the population mean. The other thing to keep into account is how much variance is within your population. So the smaller the variance in the population, the more probable it is that your sample mean will be close to the population mean. If you think about it, if you don't have a lot of variance in there, then it's going to be even more probable that your sample mean is going to be close to your population mean. So let's take a look of standard of error. Okay, if we have only one score, okay, it goes up way high. If we have 100 scores, then our standard of error goes way down. Here's an example of distribution of scores versus sample means. Okay, so the first one is an original population of IQ scores. We have a sample of N of 25 scores. Okay. Is your second example. Okay. And then your third is the distribution of sample means of all possible random samples of an N of 25 IQ scores. All right, so the primary use of the distribution of sample means is to find the probability associated with any particular sample, or your sample mean, right? So proportions of the normal curve are used to represent probabilities, and a z-score for the sample mean is computed. Okay, so chapter 5, we covered what is a z-score and how does it work. Chapter 6, we looked at z-scores for specific scores within a population. Now we're looking at how you can apply a z-score to a sample mean. Okay? So if we had a population mean of 500, okay, and we had a standard of error of 20, then that graph represents, this would now be the tail. Okay. All right. So a z-score for sample means a little bit different. Okay. The sign tells whether the location is plus or above. Okay. The number tells the distance between the location and the mean in standard deviation or standard error units. So your z formula for a sample of means, remember we had a z formula for scores in a population. Now we have a z-score for sample means. Okay. The top part remains the same, basically. Instead of your value, now you have your sample mean, okay, minus your population mean. The key thing that's going to change, this is still one number, now it represents the mean of your sample, is this standard of error. And if you recall how to calculate that, let me go back, it's in your PowerPoint here. Okay. is, well, we'll find, I'll give you another example. I'm not going to click through all of this here. All right. So if we want to look at the middle 80% of the distribution of sample means, okay, we can look at plus or minus 1.28, and we know 80%, there's 80% of all of our samples, we're going to have a mean somewhere within this area. Okay, we're pretty confident at that. All right, so we have a population that has a mean of 60 with a standard deviation of 5, okay? And the distribution of sample means for samples with a size n is selected from this population. What would your expected value be? Okay, and that is 60. It's kind of a trick question, because if you have a population mean of 60, then we would expect the value of our sample to also be 60. All right, so the shape of a distribution of sample means is always normal. Is that true or false, you think? And the next one is, as sample size increases, the value of the standard of error decreases. First one's false. The shape is only normal if the population is normal or your n is greater than or equal to 30. The sample size is in the denominator of the equation. So as n grows larger, standard of error decreases. A little bit more about standard of error. There will usually be a discrepancy between your sample mean and your true population mean. Your discrepancy is called sampling error. The amount of sampling error varies across your samples. So the variability of sampling error is measured by the standard error of the mean. So this is just a visual. If all of these little squares equaled samples, this would be how many times our samples would have the exact same mean as our population. And there would be some odd times where it might fall, our mean might fall way out here. But for the most part, we find that a typical distribution of sampling means looks very similar to a normal distribution. Okay, but look how it changes. If we have an n of 4 and a standard error of the mean of 20, okay, which is basically adjusting your standard deviation, right? Then look at an n of 4. Look at an n of 100, okay, with a standard error of the mean of just 2. See how close it gets to your true population mean? So the more you have in your n, and the larger, or I'm sorry, the smaller your standard error of the mean, the more likely it's going to be the true population mean. So in the literature, journals vary, but again, they typically refer to standard of error as SE or SEM. It's often reported in a table along with your n and your mean for the different groups in the experiment, and it can also be added to a graph. So those are the key things to take away from chapters 5, 6, and 7. Again, chapter 5, why is the z-score important? What is it? How do we calculate it? Chapter 6, what if we have a population and we're looking at a particular score? Chapter 7, what if we don't have a particular score, but we're looking at the means of a sample and making probabilities with that? So those are the key things to take away from those chapters.